Lewis uses a 20-centimeter long wrench to turn a nut. The wrench handle is tilted 30 degrees above the horizontal, and Lewis pulls straight down on the end with a force of 100 newtons. How much torque does Lewis exert on the nut? So in this example, we're going to first mark our pivot point. So that's our pivot point. And we're going to label R. So our point goes from the pivot point out to where the force is, and then we can extend it out a little. So this is the direction of R, which I'm going to label as R hat. This is the vector R, and the length we'll use in the problem, and then R hat is just the fact that R points in that direction. So we can do this problem three different ways. The first way is we can use the equation for torque, the mathematical equation, where we have torque, which is a vector, is equal to R, the moment arm, cross F. And this is the cross product. And so the cross product, we can use the mathematical definition. So that's going to be equal to R, F, and then the sine of the angle between them. And so if I look here, the angle between them is going to be the angle marked in blue. So this is my angle here. So we're going to have, that's going to be angle phi. And so we can plug those numbers in. So tau is equal to R is equal to 0.2 meters. F is equal to times 100 newtons, and then sine of 120 degrees. And so when we do the math, we get torque is equal to 17 Newton meters. And then to determine the direction, we can see here that the force is down. So we've got the force is down like this. And so we can tell if we pull the end of this wrench down, we're going to get a clockwise rotation. So it's going to be going that way. And so clockwise is a negative direction. So we're going to call this clockwise. I'm going to call this clockwise. Or we could say that torque is equal to a negative 17 Newton meters. Both of these represent the correct answer. So that's the first way that we can do the problem. The second way that we can do the problem is we can look at the same idea. Torque is equal to R cross F. And what R cross F really means is that that we're taking the vector R and we're looking for the perpendicular component of F. So we're trying to find the perpendicular component of F to R. And so I'm just going to erase some of the things I drew here. Okay, so in this case, what I'm looking for, if this is my R, so this is my R, right? And if I think about the perpendicular component, my perpendicular component is going to be this part of F, where this is my right angle. And so I need to figure out the angle that I have inside here. So right in here, this is the angle that I'm looking for. So this angle theta, how do I find it? Well, if I extend this little triangle over, I know that this is this triangle is a 30, and then this is going to be 60, and this is 90 because this is a right angle. And I know that the angle between R here, this is a 90-degree angle. So then this angle right here has to be 30 degrees. Okay, and so if I want to find this side here, this is the perpendicular component of F, the perpendicular component of F to R, then I need this side right here. And so this side is going to be F cosine of 30. So now I'm going to use tau is equal to R, and then F cosine 30. That's going to be the, let's rewrite this just for a second. So I'm going to write this a little differently. And so I'm going to say R cross F is R, and then F perpendicular. And that means perpendicular to R. And so I can write that as R times F cosine of 30. And so this is my perpendicular component. And so tau torque is equal to 0.2 meters times 100 newtons times cosine of 30. And when I work that out, I get 17 Newton meters. And again, we can see that the rotation is the same. So this is going to be clockwise, or we can say it's equal to a negative, whichever we prefer. The last way that we can look at this problem is we can say that our torque is equal to R cross F. Forgot that one. And so now I'm going to say tau is equal to, I'm going to say that I'm looking for the R that's perpendicular to F. And so if I think about what that is, that's called the moment arm. So this is going to be my moment arm. So if you look at my R, let me just erase everything again. Okay, so my R is from here to here. And so this is the triangle, right? So this is if this is R, this is the component of R that's perpendicular to F, right? So this is my F, so this is the perpendicular component, so I'm looking for this, which is called the moment arm, or D. So I'm going to say this is going to be R perpendicular, meaning perpendicular to F, times F, which is equal to, in this picture, D, or the moment arm, times F. And so tau then is equal to, so the perpendicular component is R cosine 30 times times F. So plugging in, tau is equal to 0.2 meters times cosine 30 times 100 newtons. And I get tau is equal to 17 meters, again, clockwise. So that's the three different ways that you can think about this problem, either mathematically, just using the equation here, right? So this equation, you can think about it as R. We have R, and then we're looking for the perpendicular component here, like this piece right here, to find my my torque. Or we can look at the third example where we're using the moment arm. So we're using the part of R that is perpendicular to F. So either of those, any of those three ways are an acceptable way to solve this problem.